A-level chemistry students, one of the main questions that you will see in paper 1 is questions related to electrochemical cells and electrode potential. So this is a past paper question. Let's go over this question to have some good exam technique and to set up some of the main rules that will help you to answer these type of questions. So in this question, they give you like an electrochemical series, and they give you the standard electrode potential for various reactions, and all of these reactions, as we know in the standard electrode potential, are going to be for the reduction reaction. Remember that the standard electrode potential, if we have one for reaction 1, is greater than the standard electrode potential for reaction 2, regardless what are 1 and 2. That means that the species number 1 or reaction number 1 will be reduction, and the one for the number 2 is going to be oxidation. So when we look here, we're going to see that at the top with the highest electrode potential, standard electrode potential, these are the most oxidizing agent, which means they are mostly going to be reduced, and the one as you go down, then the reducing power will increase, and they are mostly going to be oxidized if they react with the ones at the top of them. So the first question, they ask you to use the data in table 3 to explain why zinc reduces an aqueous solution of VO2 plus ions to V2 plus ions, but not reduce it any further. So let's have a look. Where is zinc? So this is the zinc equation, and this is the electrode potential. That means that zinc will be able to reduce everything above it, but not anything below it. So zinc itself will reduce all of these species above it, but will not reduce anything below it, not reduce these ones. So let's have a look at the equations. So the vanadium 2 plus is produced here. All right, and then vanadium is produced down there. You can see that the standard electrode potential for zinc will get us only until the vanadium 2 plus, but the vanadium 2 plus to be reduced to vanadium, it's not possible with zinc because the standard electrode potential here is lower. So your answer will be only related to the values of the standard electrode potential. So you're going to say that the standard electrode potential for the V3 plus aqueous to the V2 plus is aqueous is going to be greater than the standard electrode potential for the zinc 2 plus to zinc, which means that this is a possible reaction where zinc can be the oxidizing agent, the reducing agent can be oxidized, and vanadium 3 plus can be reduced to vanadium 2. However, the standard electrode potential for V2 plus to vanadium is less than the standard electrode potential for the zinc 2 plus to zinc. So in this reaction, zinc 2 plus is the one that is going to be actually reduced, and the vanadium is the one that is going to be oxidized, but not the other way around. And then the next question is to identify the species in table 3 that can reduce an aqueous solution of vanadium to O2 plus to vanadium. So only look at the metal, or only look at the substance or the species that has a standard electrode potential that is less than the one for vanadium. So you can see that the only one below it is magnesium. So here it's magnesium. So magnesium has a standard electrode potential less than the standard electrode potential for the reduction of vanadium 2 plus to vanadium, which means that magnesium can actually be oxidized and the vanadium can be reduced. And then they give you a question about two half cells, which are the iron 2 plus aqueous to iron solid, and vanadium VO2 plus aqueous to V3 plus aqueous. They are connected together, and they want you to calculate the EMF of this cell and give the conventional representation of the cell and give a half equation for the reaction that occur at the negative electrode. Let's start with the EMF. So let's have a look at these two reactions first, so not to get confused. So the first reaction is the VO2 plus, this is the one that gives you the vanadium 3 plus, and the other one is the iron 2 plus to the iron. You can see that the iron 1 has a standard electrode potential less than the vanadium VO2 plus, which means this is the one that is going to be oxidized, and then the vanadium will be reduced here. So that means that the EMF, when we calculated, we will put the standard electrode potential for the reduction reaction minus the standard electrode potential for the oxidation reaction. So now it's going to be 0.34 minus 0.44. So the EMF here is 0.78. So it's 0.78. And then the cell representation. For the cell representation, we always start with the side where the oxidation takes place. You always start with the electrode. Here, the electrode is going to be the iron, which is the solid, so FeS, and then it's going to be the iron 2 plus aqueous. So this is on the left-hand side, and then you're going to have the salt bridge, and then we're going to start with the reduction reaction. So we have the VO2 plus aqueous, and if you look at the equation, you're going to find that there is also hydrogen plus aqueous, and then we have the vanadium 3 plus aqueous. And then don't forget at the end to add the electrode, and the electrode here will be the platinum solid, even though they didn't actually mention the electrode, but in this case you can put it as platinum because in this reaction you don't have a solid which can be used as an electrode, so you're going to put the platinum as a solid. And then the half equation for the reaction that occurs at the negative electrode, it will be the oxidation reaction, which is the iron, so this is Fe, the solid, that will give you the Fe2 plus the aqueous 1 plus the 2 electrodes.